Hi, I'm now showing you the last bits of proofs for this big theorem about LP convergence and uniform integrability. So here is the big theorem we're proving, and I'm going to do in this one, I'm going to do 4 implies 2 and 5 implies 1. And now it's getting an entangled mess. But if you're still able to follow all the arrows, then we essentially did all of this except 3 is equivalent to 1 and 2. We did 1 and 2 implies 3, but 3 implies 1 and 2 we didn't. That's Sheffield's theorem. Other than that, the whole thing is now going to be ready. Okay, so let me start with 4 implies 2, proof of that. Okay, so what is 4, what is 2 again? 4 is that the supremum of the Q norms is finite. So we have boundedness in LQ for some Q larger than P, and then this will imply 2 that we have P's power uniform integrability. Okay, that's what we're doing now. Okay, let me start off with the following thing. Well, we want to do P's power uniform integrability, so we are looking at the xn to the P power under the event that xn larger than or equal to C, and we want to show that we can make this arbitrary small uniformly in n just by picking large enough C, assuming that we have boundedness in LQ. So assuming a boundedness in LQ, we can make this as small as we want just by taking C high enough. Alright, now what is this expectation? So this expectation is, let me this time write it out properly, xn to the P times an indicator. And I think about this indicator as yet another random variable. Okay, xn to the P is a random variable, the indicator is a random variable, and I'm thinking of this as a product of 2 random variables. As such, I'm going to be able to apply a Hölder's inequality on this product. And I'll tell you the exponents I want to use in Hölder. So I'm going to call P Hölder Q over P, which is larger than 1. So P is the P's power we're looking at. So we're trying to prove P's power uniform integrability, that's what P is, and we have in our assumption boundedness in LQ, so that's what Q is, and Q is larger than P according to the assumption, so Q over P is larger than 1. Okay, so what is then QH that comes with this? Let's quickly do a calculation on that. So in Hölder's inequality, I hope everybody remembers that we want these exponents to be larger than 1, and they want their reciprocals to sum up to 1. So that can easily be solved for QH. QH is going to be the reciprocal of 1 minus 1 over PH. Or if you want, PH over PH minus 1. Let's put in what PH was. Q over P over Q over P minus 1, or just multiply top and bottom by P, Q over Q minus P. So that's going to be QH in Hölder's inequality. Okay. Now let's then actually apply a Hölder inequality. So this thing here is less than or equal to, so what is Hölder? Hölder tells me that I need to take the expectation of my original random variable, the first one, which was xn to the P. I'm going to take that to the P Hölder power. This is still all under the expectation, and then outside the expectation I'm taking 1 over P Hölder. And then I have to multiply that with the expectation of my second random variable to the Q Hölder power, and then a 1 over q holder on the expectation outside. So again, these things are inside the expectation, the 1 over p is outside. This q power is inside the expectation, the 1 over q is outside. All right. Now let's work on the second bit first. So what is the expectation of an indicator? No, first of all, what is the power of an indicator? What is a q power of an indicator? Indicator is 0 or 1. 0 to any power is 0, 1 to any power is 1. So actually this power qh doesn't change anything with the indicator. Because it's 0, 1 valued, it's like it's not even there. So I can forget about qh, it doesn't do any change in 0, 1. Expectation of the indicator is a probability. So what I see underneath here, underneath this 1 over q power, is just the probability that xn, and I forgot to put in mods. I want mods everywhere, sorry. I want to add in the mods, which I forgot. Okay, mods everywhere. So it's the probability that xn is larger than c. Because you collapse the expectation on the indicator, it becomes a probability. And what I'm going to do here is I'm going to write this. These are positive numbers. So I'm going to, and you see in a second why I do that, I'm going to raise this inequality to the q power. C is positive, the mod is positive, so the mod is larger than c if and only if its q power is larger than the q power of c. And it's a positive random variable, at least non-negative random variable, so I can apply a simple Markov inequality on that. A simple Markov inequality on that reveals that I have expectation of xn to the q divided by c to the q. Okay, so it's a Markov inequality combined with this q power that I'm going to apply on here. Okay, now all I need to do now is to plug in what p holder is and q holder is. So p holder is q over p, so I'm going to put the reciprocal of that outside and p holder inside. Okay, so I have a p power and I have that to the q over p power, so that just gives me a q power inside the expectation. So I have a q power by collapsing p and ph. I have a q power inside the expectation. All of that is raised to the 1 over ph power, which is going to be a p over q. That's my first term. The second term, I have a bound on the second term, so this is going to be a bound. On the second term, I have the bound of expectation of xn to the q over c to the q. So I'm going to put that in. Expectation of xn to the q, this q power is inside the expectation, over c to the q. All of that is raised to the 1 over qh power. All of that is on the 1 over qh power. So what's that? That's q minus p over q. Okay, so I notice that underneath the expectation is the same thing. It's just different powers on it. So I'm going to have the expectation of xn to the q. That's the same in the two terms. All of that is raised to the p over q power, and then add to this power q over q, which is 1, and subtract p over q. So these p over q's actually cancel out. I'm left with q over q, which is 1, so I just have the first power of that expectation. So that's nice. And then I have to divide that by c to the q power and then this q minus p over q power. So that gives me a c to the, multiply these together, q minus p. So that's what I get. Q minus p is positive, okay? And the expectation of xn to the q is uniformly bounded. The supremum of that, well, that's the q norm, so there is a 1 over q power, but that really means that the expectation of xn to the q is uniformly bounded. So I have a bound on this. This is smaller than some number k, whatever the bound on the q power was. divided by c to the q minus p, which is a positive power. So if now I take a c large enough, then I can make this as small as I want, and that's exactly uniform integrability. There is no n dependence on the right hand side, so I can as well take a sup in front of the whole business. It's still smaller or equal to that absolute constant over c to the q minus p, which I can make arbitrarily small. So I can make this smaller than epsilon if I pick c large, if c is large enough. And that proves uniform integrability under the assumption that the supremum of the q norm is finite, which was number 4. Okay, so under this assumption. Okay, and then finally I'm going to prove that 5 implies 1, and that I don't need to, for that I don't even need to write anything, because I just need to refer to, again, that version of dominated convergence. I have improbability convergence of xn to x, and I have a dominating random variable in LP which dominates the xn for all n, and it's integrable in LP, and dominated convergence then will make sure that this improbability limit can be taken out of the expectation, and I have the convergence in LP. So all I want to do for this very last bit is I'm just going to say this much. So for 5 implies 1, 5 implies 1, all I'm going to do, I'm just going to say it's a simple application of dominated convergence. In fact, that version of dominated convergence which works with improbability as an assumption.